Okay. Okay. Cool.
Yeah, I'm just going to share.
Okay, I think we're all set. You can make it full screen, yes.
Okay, cool. Then I think we're good to go. Yeah, so this week we have Soubhik visiting from NYU. He did his PhD in Maryland, and then first postdoc at Berkeley, and now he's working at NYU. And he's going to be telling us about rare processes that can lead to CMB hotspots or early galaxies.
All right. Yeah, so thanks a lot for having me. It's been a lot of fun here. And thanks to all of you for joining. So today I'm very excited to talk about rare processes during inflation. By rare processes, I mean particle production processes that can take place during inflation, but in a very rare fashion. So there are only a few particles that could be produced, but nonetheless, they can give rise to striking signatures, either on the CMB or in the context of galaxy formation by leading to galaxies which would form earlier than what you would expect based on lambda CDM. So the CMB part of the story, which I'll first focus on, will be based on these two papers, and then I'll also talk about briefly about the galaxy formation part, which is something that we're working at the moment. Okay, so let me first give some motivation regarding the kind of physics that can lead to these sort of signatures. So first of all, of course, the LHC, along with other experiments, they have given us very, very powerful probes around the multi-TeV scales. We know a lot about how various standard model particles interact among each other. But if you take a very, very top-down perspective, then we do not have a good idea of what happens at very, very high energies. Okay. For example, we do not know if there are new particles that are present at very high energies. We also do not know what kind of symmetries there are that can govern their interactions. For example, the other question that we do not know is whether the interactions that we see at low energies, whether they continue to remain separate or they can get unified into some bigger interactions at high energies. And finally, we do not know what the identity of dark matter is and how it is produced, for example. And it could be possible that physics at very high scale has intimate connections with dark matter physics. For example, maybe that's how maybe the dark matter interacts with the standard model with some very high dimensional operators that you can get by integrating out very heavy particles. So with this in mind, the good thing is there are these puzzles about very high energies, but there are also some very, very well-motivated targets that we have at high energies. And one very interesting fact is that if you just look at the standard model gauge couplings, and if you look at its running as a function of energy, you see that these interactions, the interaction strengths, they become very close to each other around some energy scale of the order of like 10 to the 14 to 16 GeV. So of course, within the standard model, this unification is not very precise. The lines, they do not exactly meet at a given point. But the fact that these interactions, they are so close to each other, it's a strong hint. And it might indicate that there are other physics that can come in at some intermediate energy scale, and that can lead to a more precise unification at these high energies. The other useful hint that we have is in connection with the neutrino masses. So we do not know why the neutrinos are so light. And the seesaw mechanism is one of the classic mechanisms that can elegantly explain that through the heaviness of some right-handed neutrino. And if you plug in order 1 values of the Yukawa couplings, then you see like this heavy neutrino would have a mass that is also pretty high of the order of like 10 to the 14 to 15 GeV. So the point is we do have some very well-motivated scenarios that can operate at these very, very high energy scales. But of course, the important question is, how can we look for these? And especially, are there any on-shell signatures that these particles can give rise to that we can look for? Now, we do have very useful probes of these very heavy physics. And the classic example is that of proton decay, which has constrained various minimal unification scenarios. But of course, these are like the proton decay, for example, it's an off-shell probe. Of course, we do not have enough energy in the system to produce these very, very heavy particles that I was talking about in today's experiments. But here is where the early universe can play a very interesting role. The point is, when the universe was younger, it could have been very hot and energetic. In particular, if you look at the current upper limit on the inflationary Hubble scale, you see that it can be as large as 5 times 10 to the 13 GeV. And that means particles with masses of this order, or even a bit bigger than the inflationary Hubble scale, they could have actually been produced on shell during the inflationary epoch. And after their on-shell production, like, they could have decayed into various final states, and they could have left their fossil records in terms of various cosmological observables, such as, for example, the CMB, or they could have left their imprint in the distribution of galaxies. So this will be the broad theme of this talk. We'll try to see how we can use these cosmological observables to map back into the physics at very, very high energies. Okay, so this would be a very unique on-shell probe of these very, very heavy particles. Now, before getting into the main part of the talk, let me just make two broad classifications regarding the classes of signatures that these heavy particles can give rise to. You can do this classification based on the masses of these heavy particles. So if the masses are, for example, somewhat lighter than Hubble, or maybe factor of 10 to 100 times the Hubble scale, then you can produce them. You can produce these particles in significant numbers. And then it can give rise to a variety of signatures later on. For example, if you have very light fields with masses lighter than the Hubble scale, they can give rise to isocurvature fluctuations on the CMB, for example. Heavy particles, they can also give rise to various features on the CMB power spectrum or in the matter power spectrum. They can give rise to signatures like oscillatory non-Gaussianity signatures, along with all of these. So this is something I've thought about in the past, and I'm very happy to chat more about it if you're interested. But in this talk, I'm going to focus on this other class where the particles are even heavier. So their masses are even larger than, much larger than the Hubble scale.
Sorry.
Yeah.
The mass range on the left there, that came from the fact that there was exponential suppression, which is given minus m squared over h squared.
Yeah, so I'm going to talk about exponential suppression. Yeah, so the quick answer to your question is that there is another energy scale in the problem, which is the velocity of the inflaton field, the homogeneous inflaton field. And that velocity, as I'll show you in a moment, is of the order of 100 Hubble. So you gain a lot in terms of the exponential suppression.
But you'll explain.
Yeah. Of course, we are not going to look for anything which is like e to the minus 100 or something like that. Yeah.
And all of these are statements about inflation, like this doesn't apply in that radiation combination. Like, I can certainly get particles much heavier than the Hubble scale in radiation combination.
Yeah, so for sure, because there you have the other scale, which is the temperature, which is typically much bigger than the Hubble scale. But yeah, I think a lot of this you can talk about in the context of radiation dominated epoch. In this talk, I'm going to focus purely on the inflationary epoch, because that gives a very natural way of generating super horizon fluctuations, which can then later on, like, you can compute that in a nice way and study the signatures. Yeah. All right. So for these very, very heavy particles, as Tony was pointing out, like, you are already in some sort of kinematic regime where you are sort of pushing against the kinematic reach that you have. So you do face some exponential suppression, and that's why the production is much rarer than compared to this case. But you gain in two ways. First of all, your energy reach is larger. For example, if Hubble is like 10 to the 13, 10 to the 14 GeV, then these masses that we are talking about, they're really at the gut scale. They're like 10 to the 16 GeV. So you gain with that. And then the other aspect is that these very heavy particles, they can give rise to interesting cosmological signatures at the later universe. And this is something I'll be talking in more detail about. Okay.
Often the way people produce the super heavy particles, because this is all right after inflation. I presume this is not during inflation, because then anything you produce gets exponentially diluted. But after inflation, the masses of the particles can be field dependent. And so what typically happens is that you do the particle production right at the point in field space where the masses are lighter than the Hubble scale or the inflationary scale. You get bursts of particle production, but the final mass that you have at the end could be super heavy.
So you basically summarize the next few slides. So I'm going to talk more about it, but exactly that point. I'll make one comment.
That's over 20 years old.
Yeah, but I'll be talking about particle production during inflation. So you will pay exponential suppression, like exponential dilution rather. But even after that, we will see like the signatures are so striking. Even if you only have a few of these in the later universe, you will still be able to see them. So this is not during reheating, this is during inflation. Yeah. All right, so with that in mind, here's the structure for the rest of the talk. So first I'll talk about these particle production scenarios during inflation. And then I'll qualitatively explain how they can give rise to these signatures on the CMB and also lead to early galaxy formation. And then with that qualitative physics with us, we can talk a bit more about how these, for example, how these hotspots can look like on the CMB, like how bright they are, in what numbers can we have them on the CMB sky, and so on. And then I'll briefly comment about how we can look for them using either CMB or using like high redshift galaxy surveys, because that's where the signatures will be very prominent. All right, so let's start with the first part. So to characterize these rare processes through which particle production can take place, we'll just make like some simplifying benchmarks or some simplifying assumptions if you want. So we'll assume that these particles, they are produced with a certain average number density. So in a given volume, we would be able to predict how many of these particles are there, but we won't be able to predict like their locations in space. Okay, so that in space, they will be completely randomly distributed. Okay, so it's something that can arise very naturally in various production scenarios. The other thing that we'll assume, again, just for simplicity, is that we'll assume that these particles, they're produced only during a certain epoch during inflation. So they're not randomly distributed in time. And you could for sure relax this assumption. You can also think about scenarios where they are randomly distributed in time, but we'll see like whatever phenomenology we learn by focusing on a single epoch, it will apply to this other situation as well. So it's easier to generalize. So with this in mind, you can ask like these three broad questions, and we'll see like these questions, they will determine a lot of the phenomenology later on. So first of all, we'll ask like what happens when you produce like one single particle, like what is the associated signature. Now, normally you'd say like a single particle itself is too weak to give rise to anything discernible. But the point is these particles, they are very heavy. So even a single particle can have an important effect. So that is something we'll study. And then we'll ask like, what is this number density? Like, can you compute it in a given model? And also we'll also make this assumption about like they happen during a certain time during inflation. And we want to understand in terms of model parameters or like what determines that quantity. Okay. All right. So now let me talk about what are the available scales that we have during inflation. So if you want, like these are your center of mass energies if you want to view this as a collider problem. So first of all, space-time is expanding with Hubble rate during inflation. So you are automatically producing quantum fluctuations with Hubble scale energies during inflation. You produce them, then they get stretched out of the horizon, they get frozen, and so on. So that's the standard story. But then there is also a second scale in the problem, which is easily said in the context of some single field slow model. So here, what you have in mind is that there is some classical field, which is slowly rolling down a potential. So this is when inflation is happening. When the field is over here, it's oscillating rapidly, and reheating is probably happening at that epoch. But you can compute what the power spectrum of the inflaton fluctuations are during that rolling phase. If you compute it, you get a relation which is like Hubble to the 4 over phi dot squared, where phi dot is basically the velocity of this rolling field. And this power spectrum is something that we later on measure via the CMB, because we do know how big the CMB anisotropies are. And that basically fixes this kinetic energy scale to be 60 Hubble entire thing squared. Okay, so this is something that we know from the CMB data. So this is a concrete number that we know. We do not know the Hubble scale during inflation, so we do not know this quantity individually. We also do not know the absolute value of this guy, but we do know the ratio, which is phi dot over h squared. So this already tells you that you have at least 2 energy scales in the problem. And that already tells us that producing something which is of the order of, producing a particle whose mass is of the order of 100 Hubble or 200 Hubble is not going to be that difficult, as long as we have some way of tapping into the kinetic energy of the inflaton. All right, so now let me just qualitatively say, like a very generic way in which how particle production can happen during a certain epoch during inflation. So what we'll imagine is that that the mass of the particle it varies with time, and one simple way it can do that, if the mass of the particle is dependent on the inflaton, then as the inflaton is moving around, the heavy particle mass can change with time. Okay? So I'll write a model in a moment, but this is a very generic scenario that can arise. And then what I'll imagine is that normally the particle mass is much bigger than this kinetic energy scale. So you do not have enough, you are basically way off the kinematic reach. You do not have enough energy. So particle production is heavily exponentially suppressed in this epoch. But then there is some time instant, which I'm calling by T star, when the mass becomes much smaller, of the order of this kinetic energy scale. And that's where you have more kinematic access, so you produce the particles. And then later on, again, the particle mass increases, so you stop producing this. So
we have to limit how deep this thing goes, right? Because otherwise you could get stuck there.
No. What do you mean get stuck there?
so this is just a
Well, it's a burst. I mean, you go through it. I mean, typically that would go to zero.
Well, I'm going to fall there.
It's not a potential.
it's not a potential, but yeah. It's just, sorry, I should have been more clear. It's just mass as a function of time.
If you want, think of it as a Yukawa coupling. No. It's think like a Yukawa coupling. So look at the top picture. If you have the field oscillating about that minimum, each time it goes to the minimum, the mass of this thing could go to zero. So each oscillation, we get a burst of particle.
Yeah. So let me write down the Lagrangian if you want. So what we want to do is to study particle production around T star. So you can do something very simple. You can say that the mass of the pi field, which is the heavy field, it's some function which is dependent on phi, and you can just do a simple Taylor expansion around T star. So there is some leading order piece. The first order piece vanishes because you're near minimum, and then there is a second order piece. So what is important here is that if you write it in this way, you immediately see that there are 3 important quantities. First of all, there is the mass the particle has at the minimum. So this is the smallest the mass can be during inflation. So I'm going to call that by M0. Then there is this dimensionless coupling, which couples the inflaton to the heavy particle. It's like a phi square chi-square coupling. It's a quartic coupling. It's positive, so I'm going to call it by G squared. And finally, there is a third quantity, which tells you when this happens. So we are thinking about single field models, so you can relate the cosmic time T star with the inflaton field value at that epoch, which is phi star. But it's often more convenient to talk about the conformal time corresponding to T star, which I'm denoting by eta star. Okay, so these 3 quantities that tell you, like, they basically determine most of the phenomenology, as we'll see later on. What is also important is that the conformal time, it also determines the size of the co-moving horizon when particle production is happening. Okay, so we'll see, like, these parameters G, M0, and eta star, they're going to play important roles in the following.
But do you know, I was going to say, how natural are these? Are you going to show these parameters to be? I mean, do you have to have them in a very small mass range to get the signal?
Yeah, so yeah, it's probably easier to tell when I have the more detailed expressions. But very quickly, this coupling will take it to be order 1. And eta star is purely a choice. So eta star in the end determines how big these signatures are. For example, if you're thinking about, as I'll tell you, like if you're thinking about spots on the CMB, eta star determines their angular size. So if you want, you can vary it freely. It would just change the radius of the spots. This guy is constrained in the sense that if it is too light, you will produce tons of these things, and your observation will rule down. If it is too heavy, then of course you do not produce them. You do not produce enough number of them because you're heavily exponentially separate. So in that sense, there is some range of M0 that you have to
be somewhat lucky.
Yes, that's true. Yeah. Yeah.
There are some juice spheres of order 1.
Yes.
May I ask, is this coupling, doesn't that cause some sort of radiative correction potential? So that.
Yeah, there are loop factors. You can, I mean, in the end, there could be some, if you want, there could be some small natural lens problem, but like it depends a bit, right? So it depends on like how you want to UV complete this guy. So I'm not going to talk about UV completion, but there, like if you, for example, do a SUSY UV completion, you can get away with like maybe a small amount of tuning, like 10% tuning. Yeah.
It's guaranteed here. There's no spoiling of the slow lowering, so slow roll dynamics of input.
So good. So you.
Take into account this.
Yeah, so good. So there is a question of radiative correction, which is more dependent on how do you UV complete. The other aspect is in some sense more dynamical, which is maybe that's what you're asking is like you might worry that when this particle production happens, whether that back reacts on the inflationary trajectory in terms of either slowing it down or making it move in some other direction in the landscape.
Much smaller number refolding, for example.
Yeah. Yeah, so for all the parameters, for all the M0, G, and eta star that we'll be talking about, these corrections will be very small, like sub%. So it's not going to mess with the homogeneous expansion. Yeah.
And that's just because you're not going to be producing very many.
Exactly. Yeah. So that's also the other. Yeah. So if you lower M0 too much, you're going to produce so many particles that you're basically going to drain most of the energy out of the inflaton, and then of course you mess with the expansion. Yeah.
Wait, so you kept saying this mechanism is going to let me produce things that are like order 100H. When you were quoting that 100H, were you talking about the mass at the minimum?
Yes.
Or the mass okay, so the like mass not at the minimum can be arbitrary, like really high.
Sorry, the mass at the minimum, that's already going to be of the order of 100H, and then later on it's going to be even bigger. So if you want like near the value over there, near the bottom, that's what M0 is. And that M0 is going to be of the order of 100. And you produce them, even that you produce with some exponential separation. And then the mass increases, and yeah.
So if I just wanted something with 100H, I don't need to do this funny thing of having it change mass. I can probably...
As far as particle production is concerned, you do not have to do that. But then we'll see like the signatures these particles give rise to, that requires a very heavy mass. So you need the mass to change with time. If the mass was always that high, then you are just not going to be able to produce these particles. So what you want to do is you let the mechanism like produce these particles, and then later on they can get heavy and give rise to signatures.
Yeah. I'm sorry, one stupid question.
Yeah.
You just produce particles when the mass is smaller
Mm-hmm.
than this particle,
Mm-hmm.
and then it will restore its heaviness. But then from where this, like based on energy conservation, I should have energy conservation. But then from where do I have increase of this energy?
Good.
Yeah.
Yeah, good. So that's a good question. So we'll see like it comes at the cost of the inflaton. So what's going to happen is that this is something I'm going to talk more about. So as these particles, they are getting heavy, they're going to slow the inflaton down. It's going to like extract the energy from the inflaton.
Like it becomes even more small, like slower than.
It's not going to get like slower by an order on amount, but I mean I shouldn't say like that. I mean, but yeah. So let me get to that. Yeah. But that's where it's coming from. Yeah. Okay. So now let me very qualitatively talk about particle production during inflation. So this is entirely like meant to be a cartoon. We of course do like more concrete computations in the paper. So the point is, we have this this scenario of changing mass in a sort of rapid and non-adiabatic way, And why this sort of non-adiabatic change can lead to particle production, you can already understand from some quantum mechanical analogy. So let's imagine you have some harmonic oscillator and you have a particle which is at the ground state. Okay, so you have a Gaussian, and this black is the well. So now what you do, let's say you suddenly stretch the well in a very, very rapid way. So the well now looks different, looks like this. But you do it so rapidly that you have not given the ground state enough time to relax. So the ground state, it still looks the same. But now what has happened is that this particular wave function is no longer the ground state wave function of this new well, but rather it's a combination of the new ground state and the new excited state. So this sort of already tells you that anytime you do something very non-adiabatic, you have a chance of producing excited states. And this is just a quantum mechanical example, but if you go through the computations in a more field theory setting, in the context of expanding space-time, you can repeat this analysis and you can compute like how many particles are produced in this manner. So for example, you can compute the probability of particle production, which has the exponential form as expected. And here you explicitly see that if M0 is much bigger than the kinetic energy scale, you pay an exponential suppression in the production probability, so you do not produce many of these objects. And then with these probability, if you integrate it over the phase space, you can also compute what the number density is. Okay, and the same exponent shows up here again as expected. So what we are going to be focusing on for our parameter space, we are always going to operate in this regime where this exponential is much smaller than 1. If you try to make M0 much lighter, what is going to happen is that these produced particles, they would back react on the inflationary trajectory and then modify the expansion. Okay. All right, so this already gives us one of the quantities that we were after, which is like how many of these particles you would expect in a given volume as a function of the model parameters G, M0, G and M0. Yeah.
Sorry,
Yeah.
Go back. Just I don't need the mass to be heavier again as time goes by, right?
So that's the next slide. Let me come to that. Yeah.
Well, fixed angular.
So good. So this tells you like how many of them you produce at the point of minimum, but then there is this this other effect that would happen if the particle mass increases, and this is related to what you were asking about. So let's now try to understand like what happens after these particles after they get produced. So first of all, we have this coupling between like this quartic coupling between phi and chi. Chi is the heavy field. So what's going to happen is that after you produce these chi particles, because of these quartic interactions, these chi particles, they're going to create a force on the inflaton field. So they're basically going to slow it down. And because of this slowing down, what is going to happen is whatever locations you produce these particles, inflation, the evolution of the classical inflaton field would get modified in those locations. It would be slower. And as a result, in those locations, inflation would end later compared to other times. Okay, so I'm going to give more equations, but this is just saying things in a qualitative fashion. Now, one thing that you do know is that if you have single field inflation, then the fluctuations of the inflaton, that is what determines the gravitational potential you get in the end. So if these heavy particles, if they are modifying the inflaton evolution in a local fashion, it's also going to change the gravitational potential wells in a very localized fashion. So in particular, what that means is that if you were to plot gravitational potential as a function of position, just in 1D, what's going to happen is that whatever random locations you produce these particles, you'll see that the gravitational potential becomes modified at those spatial locations. So if you move far away from this location, the potential takes the usual 1 part in 10 to the 5 value, but then around these locations, there is some order 1 modification. Okay. And as you're asking, like this modification is basically coming at the cost of extracting energy from the inflaton. Okay, so you're slowing down the inflaton, and that's how that is basically what is compensating the increase in mass for the heavy particle.
The local enhancement of P zeta because of the small volume.
Exactly. Yeah.
Can I actually ask a question about the adiabaticity thing? So it seems like the important thing is that I go through this dip in mass very quickly. So it seems it's got to be something like the time it takes me to go through that has to be much less than Hubble or something like that.
Yeah, that's right. That's
So
right.
I understand where phi dot should be relevant for that. I would also think that the size of the dip, it should be relevant. Is that showing up in this formula somewhere?
It does. So good. So it is basically good. So everything is determined by the motion of phi. So phi dot is a much larger energy scale. So if you convert that into time, it is indeed a shorter time window compared to Hubble. And the fact that you have like this order one value of the coupling, that still ensures. So in other words, like unless you're messing with the homogeneous expansion, inflaton is not going to get stuck around phi star for a long time. It's just rolling along as always, and its rolling speed is much higher, much larger than the Hubble expansion rate. So it's still in that sense a very small time compared to compared with the Hubble scale, for example.
I guess I'm just saying, if I called that width of that thing delta phi, I would expect delta phi to appear in your formula somewhere.
It appears via phi dot. Because delta phi is like phi dot times t.
Yeah.
So you have to, of course, like you have to see like how big the t is. But yeah, that's how like phi dot appears. The delta phi itself doesn't appear. Yeah. You can, so I mean, I don't have an expression for that, but one thing you can do is you can, for example, track, if you try to evaluate this guy, for example, as a function of time, you will see like there's a certain time where the probability peaks and then again it falls. So yeah. And that width is much smaller than Hubble.
Sorry,
Yeah.
do some people use this for setting PBH?
Yeah, good. So we are not going to have as much of an enhancement in the delta over rho. It's going to be only order one. Yeah, PBH is like, yeah, I mean, if you want to phrase it in terms of this coupling G, for PBH, you would need G of order 10 to the 5, which is not what I'm going to do. That's also very interesting. So in terms of the, so that's something we have not explored in detail, but this is again that assumption I was talking about. I'm going to focus on a single epoch of production. If you produce them at multiple epochs, that's for sure very interesting. What's going to happen is that I'm going to talk about the hotspots in a moment. So you'll see hotspots of multiple radii, because each of the radii, it depends on the horizon size, like the co-moving horizon size when you produce. So if you produce them at multiple epochs, you will see multiple radii at the same time.
But there is nothing in the production that I have to change much.
Right, exactly. Yeah. Yeah.
So maybe lumps will be the same.
Right. As long as each lump does not extract a lot of energy from the inflaton. Yeah.
There is no parametric.
No.
Isn't there something called trapped inflation, which is basically like doing this a bunch of things?
It's it's something in some sense that's a more extreme version of this, where the inflaton really like gets trapped. The dissipation is so much that you are again like modifying its evolution. But this is a very gentle modification if you want. The motion of the inflaton is not changing at all. Like if you were just looking at, like if you had a way of looking at the motion of the inflaton, you won't notice a difference. Yeah. All right, so now let's see what's going to happen at late times with this gravitational potential. So what we'll consider is that after inflation, the universe gets reheated, it's filled with some thermal plasma. But then there are these random locations in space where you have these potential wells. So what's going to happen is that these wells, they're going to trap more plasma compared to the neighboring regions where the wells are not that modified. So then once CMB gets decoupled, these regions, because they had more photons trapped, they're simply going to emit more photons compared to the neighboring regions where there were lesser photons to begin. In other words, if you were to make a map of the 2D sky using some satellite like that, you will just see some random locations where you see anomalously larger amount of photons coming towards you compared to the neighboring regions. Okay. So in other words, you would expect to see hotspots on the CMB sky. Now I'm glossing over some of the details here. I mean, what is in the end important is also like both the photon, like the photons, they redshift as they move out of this world. So you have to take into account this like Sachs-Wolf effect and so on and so forth. But qualitatively, this is what would happen. Yeah. Yes. This would be on top of that, and that's going to pose a challenge in terms of detecting them. So I'm going to talk about that after a few slides. Yes, but exactly, it's going. Yeah, so that itself is a pretty important and interesting question. So I'll talk about a very simple, if you want, like a cut and count method. It's basically motivated by collider physics in terms of looking for these hotspots. But you can also do more sophisticated analysis. Yeah. But the quick intuition is that you still want the spots to be at least order 1 or more brighter compared to the average hotspots that you see.
This law contains many.
Sorry, I could not hear.
Law that contains many spots, not just one.
Good. So it is seeded by only one particle. But the effect of this, so what's going to happen is that after a single particle is produced, you are going to affect basically a lot of cosmological modes which have the size of the horizon at the time of production. So the width of this spot is basically determined by when you produce them, like what is the angular scale corresponding to the horizon size at that time.
So it's through perturbation.
Yeah.
So like when I went through that dip in mass,
yeah,
like I basically only produced 0 or 1 particle.
At a given location, yes. Yeah. But you have, of course, like across the entire sky, you'll have multiple of these. All right, so now let us see how, so I talked about the CMB, but these are like the same physics would also give rise to interesting signatures in the context of galaxy formation. Now, this is, of course, like galaxy formation itself is a very nonlinear process. And if you want to do something very quantitative, you have to do numerical simulations. But just to compute like some qualitative effects, like how early do you affect galaxy formation and what are the masses of the associated halos, you can get a lot by just doing some simple, just following some simple analytic methods, for example, like the fresh factor formalism. So let's imagine you have some sort of a map of the matter over density, so delta over rho. Here I'm just drawing a 1D plot, so I'm just plotting delta over rho as a function of x calculation. Now, generally it has these wiggles. So there are regions where you have overdensities in matter, there are regions where you have underdensities and so on. But what the simple analytic formalism, what it relies on is that it says anytime the delta rho over rho, it passes a critical threshold, you would later on form halos in those spatial locations. Okay. So in the context of this particular picture, like you'll eventually see the halo over here, here, and here, for example. Okay. Now, this is a very, very simple model. It just says like as long as the overdensities are sufficiently overdense, you will host a halo after subsequent evolution. But it turns out that it's very, very well like numerical simulations, like whatever analytical computation you do starting with this assumption, it matches very, very well with more dedicated numerical simulation. So for our purpose, this would be totally fine. But now let us try to understand what these overdensities or gravitational potential wells do in the context of galaxy formation. So here is the usual evolution history of a single Fourier mode. So I'm just talking about lambda CDM, just standard cosmology. So a single Fourier mode during matter domination and within subhorizon scales. So what's going to happen is that during matter domination and at subhorizon scale, this Fourier mode is going to grow linearly with time. Sorry, linearly with scale factor. And then starting with some initial value, which is of the order of 10 to the minus 5, eventually there will be a time when this mode has grown to that critical threshold. And that's when eventually it will see the halo corresponding to size of that particular mode. Okay, so this is just a simplistic way of saying like when galaxy formation would happen given a certain given a mode of certain size. And this is something you can compute in lambda CDM. So now let us see what happens in the context of these additional gravitational wells that come from particle production. So the evolution of a given mode is exactly the same as before. So there is this linear growth with the scale factor. But the point is, you started with an overdensity that is larger from the standard lambda CDM prediction by some factor G. Okay. So this G is so I'm going to show you in a minute, but this G is the same coupling that appeared earlier in the Lagrangian. So now what's going to happen is something very simple. So you are larger from the standard prediction by a factor of G, and as a result, you are going to hit the nonlinearity scale, which is delta C, correspondingly sometime earlier. Okay, so you're going to reach that scale a factor of G larger in redshift. So what that means is that if you have these additional overdensities, it's going to lead to structure formation at an earlier redshift compared to what you would have expected from lambda CDM.
But then G necessarily has to be bigger than 1.
Yes.
But then your potential now is you've got G pi squared chi squared.
Right.
With a big coupling.
That's right. So
Correction.
yeah. So there is still the aspect of radiative corrections. That's true. So with respect to radiative corrections, I would say we have not investigated the UV frameworks, but potentially you can embed it in SUSY in some way. With respect to modifying the inflation motion, it's still fine to have G larger than 1. Like you still do not.
That's okay. I just worried about lifting the potential.
Yeah. So that's something that we are also actually with me. We're right now thinking about whether if you do it in some sort of hidden sector or some spectator sector, whether there is a way of getting away with G order 1 or smaller. So that's a bit of model building that we are thinking about at the moment. Yeah.
Sorry, do you want G order 1 or larger just so that you notice that it's sufficiently like earlier than it should have been?
Either is it sufficiently earlier in the context of galaxies or it's sufficiently hotter in the context of hotspots. Yeah. But in the end, you still need like for this purpose, even like having G's of order 2 or 3 is fine. And that's also true for hotspot. But we are working on the model building a bit more to see if we can go to lower values of G. Yeah.
Are these things stable?
They need not be stable. So you want them to like get reduced, but then they affect the curvature perturbation when they're produced, and these curvature perturbations they eventually like exit the horizon and get frozen. So they would carry all the imprint of these heavy particles.
Also, it wasn't clear to me when they're being produced relative to the end of inflation.
Yeah, good. So I did not talk about it. But just to give you a number, I'll be talking about, like, for example, let's say when an L mode corresponding to 100 exits the horizon, L mode of 100 in CMB, that could be one representative time when these particles could have been produced. So these are all happening like during the CMB time or just after that.
So during the last 60 fold.
Yes, for sure. Yeah. If you produce them too early, if you produce them too late, the sizes are too small for experimental purposes. If you produce them too early, the danger is that you are not going to see many of them because they're just like diluted too much, and also, yeah, those effects would be pretty strict.
So, and I guess that's what your phi star is.
That's right.
So
Yeah.
phi star, and phi star normally we refer to phi star as being the beginning of the last 60 equals, but we can call that phi 60, and
Yeah.
phi end is when the accelerated expansion ends.
Right.
So you're having, how accurately do you have to choose phi star?
Yeah. So you have to. Yeah. Good. So the CMB modes, they see like order 10-ish e-foldings roughly. So you have to be within that regime roughly if you wanted to have a signature on the CMB.
Well, I guess that would.
I
If you draw a big picture of the potential, the
Yeah,
inflationary
yeah.
potential, right? So you had it earlier, but
Right.
I mean, it's basically flat and then you have the minimum.
Right.
So it's sort of before it starts dipping.
Yeah, I'd say it's still much close to.
Draw it again, it's been easier.
Yeah, let me go back over here.
There.
Yeah. So yeah, I mean, if you call so if you call like the beginning of that gray line over here 560, I'd say it's still pretty close to 560. Like it's not too
But the
far.
question is, how accurate does that have to be? That is, how specific do you need it to be?
You just want the signature, like it's like, of course, like from the physics perspective, production could happen at any time. But if you wanted to use like CMB as proofs of
It's your
these,
potential, it's your coupling that's determining it, right? You're introducing, I mean, it's not really a phi squared chi-squared coupling, it's a little bit more involved with that so that you get
right?
that the minimum, that there is a minimum of the mass. Right?
Yeah,
So
yeah,
that
mhm.
You have some phi minus phi
That's
star.
right, yeah.
Right.
Yeah.
In that, right? So that's what I'm asking is how specific that phi star has to be. So if phi 60,
Yeah.
at the beginning of the grade, let's
Mhm.
say it's 5 times n blank.
Yeah,
Okay, and end of inflation occurs at n blank.
right.
So you have between 1 and 5 n blank,
Yeah,
and you're saying it should be around 4.5.
yeah, something like that. Yeah,
But
yeah.
is 4.4 not okay?
Yeah. So good. So I don't have good. So I don't have a number in mind, in the sense that in terms of e-foldings, I can tell you, you have to be like within that 10 e-folding. So it depends on how phi is evolving as a function of n.
35 and 45?
Yes, yes, for example. Yeah. All right. So good. So let me just summarize. So far I've discussed about how these particles, they can get produced during inflation and leads to these signatures. So let me now briefly talk about how they would look like. And for this purpose, I'll mostly focus on the hotspot story, because it's just a bit easier to show with pictures and so on. Okay, so let me now get into a little bit of more quantitative details regarding how this coupling G appears. And of course, we're interested in how overdense the regions are, or like how hot the hotspots are actually. So for that purpose, what you can do is you can, for example, write down the action for this massive particle, which is giving rise to this modification in the potential. There is, of course, like the leading order term that we always write, so just mdt. But there is a subleading correction that comes from the metric factor G00. Now, G00 itself is not a dynamical degree of freedom, so you can write it in terms of the curvature perturbation, which appears in the spatial part of the metric. So that's what I'm calling by zeta. And if you just solve the Einstein equations, you'll see like there is the second tadpole term, if you want, that is linear in zeta, that comes with this mass term. So this is basically the statement that if you have a mass, it would give rise to a contribution in zeta. Okay. So now to estimate how big that contribution is, you can write down the tadpole term, and then there is also the usual kinetic term from the inflaton. So you can write the inflaton fluctuations in terms of zeta. So there is some conversion factor here. But now you have something with a linear piece and a quadratic piece. So you can, if you want, you can extremize, and that will tell you like the curvature perturbation associated with this massive particle is given by a quantity like this. So there are some extra factors of H and phi dots, but what's again important is it does like linearly grow with M. So this is the reason why you want the M to become larger post the production time. Okay. So of course the question is how big these zetas are, or how big this curvature perturbation is compared to the standard fluctuations that you produce during inflation. Now, of course, that we can quantify by considering like some RMS fluctuations of the inflaton, and that is the number, that is the parameter we get, Hubble square over phi dot. This is a quantity that's supposed to be like 1 part in 10 to the 5, but I've removed some factors of 2 and pi, so it's a bit bigger, like 3 times 10 to the minus 4. So now you want to just take the ratio of zeta sourced by a particle versus the zeta coming from these fluctuations. And if you go through the algebra, and if you plug in the time-dependent mass coming from this Lagrangian that we had earlier, so here by mu I just mean G times phi star, so it's the same Lagrangian as before. Then you will see like this ratio of zeta is just given by this parameter G. Okay? In other words, like these two factors, they cancel as far as like other than leaving a factor of G. So what it tells us is that if you have G of order 1 or a bit bigger, then you already have a chance of seeing these associated overdensities, because these overdensities, they are now as large as the standard fluctuations. You don't have to go to very, very large values of G, for example.
Wait, so
yeah.
Now it looks like the mass has a factor now, though. Like,
so this is so good. So you're talking about this guy? Or
Oh, I guess there's G in there. Well, I was kind of saying, can I like fix G and take M to be small or something like? But I guess not, they're related, so.
So this is the mass after the production has happened. Yeah. So so you can of course like you can make G. I mean this guy is fixed with respect to Hubble from power spectrum. So yeah. So if you vary G, M will also change accordingly. Yeah. Okay, so the main upshot here is that you want this order 1 values of coupling, or probably a bit bigger, and then you are in business as far as observations are concerned. Now let us see how they would look like on the sky, the hotspots. So here one interesting aspect is that you're producing these particles from vacuum. So if you produce one particle with a certain spatial momentum, you're also going to produce another particle so that they are back to back, just to conserve momentum. So you're going to have these particles always come in pairs. So you if you see a hotspot, then you will also expect to see another hotspot close by, so far as you can distinguish between the two. Now I've just drawn some mock images like how they might look like on the CMB sky. Of course, I have not drawn the standard CMB itself, but you'll see like the distance between the two spots, they're a bit different compared when you look at one pair versus the other pair. And this distance itself, it's a bit of a random quantity. Like it varies between they can be very close to each other, or they can also be separated by the horizon size at the time of production. So there is some variation there, and we account for it by just taking it to be some uniform distribution within 0 and the horizon size. All right, so with that, you can also like zoom in, and this is something we computed.
Aren't they produced basically at rest?
Yeah, so they're primarily produced at rest, but again, like if you want, you can think about some Z2 or some Z2 symmetry.
I find it producing two of them, but aren't they both right next to each other?
Basically right next to each other, but then it's a bit harder to quantify. Like in some sense, some of them could be produced semi-relativistically, so they might move around a bit, maybe in the next folding or so. So there might still be some separation between the two pairs. Yeah, we were not able to like compute that separation super precisely, other than saying it's either they're on top of each other, or they're separated, or they're within the horizon. Yeah. And that horizon restriction is just coming from just from causality. Yeah. Yeah.
Yeah, there. So that expression is the one sort of in the middle. That's the thing that's giving you your mass. So
yeah.
So M0 is small.
M0 is of the order of square root of phi dot. It's much smaller than M. M0 is
and so mu is big here.
Sorry, mu sorry is a abuse of notation. So mu is just G times phi star in terms of the previous equation.
Right. So
yeah. So mu is for sure much bigger. It's of the order of G times phi, and if you have like phi to be like 10 m Planck or 5 m Planck, then mu is also of that order. Yeah. But what does matter though is the difference, right? And the difference is much smaller compared to this case.
But yeah, I see that when phi is mu over G, then that's when you're producing.
Right. Mm-hmm.
The moment that
yeah.
you make the production.
Yeah. All right. Good. So you can also zoom in on one of these pairs, and this is something we computed in the paper. So you start with the initial curvature perturbation, then you take into account the subhorizon evolution with the transfer functions and so on. And with that, you can compute the radial profiles. So for example, this is like if you want the center of the hotspots, you could compute like how the temperature would vary as you go from the center to the outer periphery. So, okay. And here, I mean, just as an example, is also related to the earlier question. So I'm choosing the time during inflation, or the horizon size during inflation, such that these spots are roughly like 1 degree on the sky. Okay, so but that's that is a model parameter, so it can vary as well. It can be smaller, it can be bigger. All right, so finally, we can also, because we had the expression for number density, you can compute like how many of them you would expect on the CMB sky. And here I have drawn the CMB surface, but it turns out like even if these particles are like, if they're literally not on the surface, even then there can be some effect. So you can consider some thin shell around the CMB to compute like what is the net number of signatures you would see on the CMB sky. And of course, like what you do is you start with the initial number density, you take into account the dilution, so the ratio of the scale factors, it has exponentials in it. And then in the end, you just multiply by the volume. And just to give you some numbers, if you think about this minimum mass being like 250 Hubble, this is the eta star. So this roughly corresponds to a degree in size, degree in angular size for each of the spots. If you take G of order 3, then you'd expect to see order 20 of these spots on the entire CMB sky. Okay, this is just to give you a benchmark value. All right, so just to summarize, as far as hotspots are concerned, these are again the parameters that determine most of the phenomenology. So you have the central temperature, the shape of the spots, and also how many of them there would be. Okay, I am running out of time, I guess. So should I just quickly go through the rest of the stuff? Or?
Yeah, maybe we started a little bit.
Okay. All right, sounds good. So yeah, let me just quickly summarize some of the detection aspects, and I'm very happy to go over more details if you're interested. So if you wanted to look for all of these, you basically have an image recognition problem. So this is a mock CMB map. This is also another mock CMB map, but in one of them you have these hotspots. Okay. Now, because we simulate this ourselves, we know which of them actually have the hotspots, and you can even see it if you stare at these two pictures sufficiently long. It turns out like there are like 3 pairs of spots at these specific locations. So what you of course want to do is to look for these things, and you can do something very, very simple. So this is entirely motivated by collider physics, because that's like the very simple thing you would do to begin with. So what you would say is that if there are hotspots, you would expect the CMB to be brighter on the average compared to the scenario where there are no hotspots. So you can do something very simple. You can put a cut on the temperature, and you can ask how many pixels would survive on a CMB sky map. And for the images that I was showing, of course, like the CMB itself, by just statistical fluctuations, it would produce hotspots. Temperatures having larger than 30 microkelvin, 300 microkelvin. But the point is, if you have these hotspots, you have more survival pixels. Okay, so all the 3 pairs would survive that cut. And with that, you can just do some simple significance estimate, and you can do a projected sensitivity of what such a simple search would do as a function of the coupling. You can, for example, say like how many of these spots can be hidden on the sky. So just to give you an example, if you focus on G of 2, you would conclude that you'd hide of the order of like 300 of these spots on the entire sky. So that's the red line over there. And of course, as you increase G, the spots themselves, they would get individually brighter, and as a result, you can hide lesser and lesser number of them. So
CMB does have hot spots like old Boston.
Yeah, you're talking about point sources, and right? Yeah, so that is for sure challenging. So one thing I have not talked about.
Is that map already cleaned of clusters, or otherwise, can you say have some undetected clusters that you say, oh wow, I have this, I see a hotspot. Therefore, I found fancy inflationary physics. Well, it can be just a cluster that is under your inflation.
Yeah, so for sure, so that could happen. So one thing that is powerful though is, so in that study, we did not take into account clusters. It was just mock CMB maps, just to give us some examples of what a search can do. But the point is, we can compute these shapes, like the radial profiles. So if the spots are bright enough, you can actually do a morphology study. And there, as like there, you can also like rely to some extent on like spherical symmetry of the spot and so on. But of course, like as the spots get dimmer and dimmer, it becomes harder to do that. And like these undetected clusters or undetected point sources, they would be a challenge. Yeah.
Do you rely on the spot tracker?
For this simple cut and count, we do not. But then we in our follow-up paper, we do rely on the profile. Yeah.
Is that profile model dependent?
That profile is actually, it depends a bit on when they're produced. And the physics is that the modes are produced at certain epoch, right? And that also determines like when the modes would re-enter the horizon. And then you have to take into account what the transfer functions are and so forth. So there is some lambda CDM model dependence if you want. So different values of eta star would give rise to different shapes. So I have some plots in the backup slides. I'm happy to go over those. Yeah. So of course, yeah, it does add some degree of sensitivity, like some degree of uncertainty if you are going to look for them. So you might have to, good. So I mean, it's basically like going into the other stuff that I didn't talk about. So if you wanted to look for them directly, you'd have to like build a big bank of templates if you want, corresponding to different types of shapes and so on. But you can also do like a neural net based approach. So that might be more powerful in terms of like taking into account multiple shapes at the same time. So we explored that a bit in the follow-up paper. But of course, like the important thing to do here is to look at an actual data and look at this undetected point source aspect, and then you would be more confident. But yeah, we have some evidence that if you use machine learning, then you can move away from this dependence on shapes a little bit at least. So yeah, so the idea is that you would train a network and it would be able to broadly capture a bunch of different shapes at the same time. Yeah. All right. So the last point I would like to make is that you can try to detect these hotspots directly by looking at the CMB power spectrum, for example. But as you would expect, like these spots, they are very much localized in position space. So if you wanted to like Fourier transform the data and compute like 2-point functions, you would wash out some of their main effects. This is just saying if you were to do a simple power spectrum based search, your constraint would be much weaker. So those are shown in like in dotted gray or dashed gray, depending on the amount of deviation you have. So this is just an illustration that you want to look for these things directly in position space instead of the standard analysis where we look for stuff using the CMB using the power spectrum. Okay. Yeah.
High enough, even higher to the same result as your position space.
Not really, no. It's you would still so I haven't like okay, so I haven't shown other examples. So we have this is eta star corresponding to 160. We also have an example with like eta star of 50. So that would move like over here roughly. And you can still say the same thing. Yeah. Like the power spectrum search would be poor. But of course, like if you go to very, very high Ls, the CMB itself also lose sensitivity at some point because you cannot resolve it super powerfully. Yeah.
So the typical size of this hotspot is solid. You see, because the position space search will still be more.
Yeah. Yeah, I think this particular cut and count search won't do as good. But again, if you do this, if you actually do a search that uses the profile, so here we are not using the profile, right? We are just putting a cut and asking like, yeah, how many pixels survive. So if you use the profile information, then you would still do better. Yes. Yeah, I mean, so the intuition is that like these modifications, they basically depend on how many of them you produce. So the net modification to a power spectrum, it depends on the total number.
But significance also depends on the total background.
Yeah. So sure, but so then it's a quantitative question. So I can discuss more. So yeah, so this particular cut and count search, I can show you the results for like 50 megaparsec in a moment, but but ideally, yeah, if you are competing with very high Ls, you want to use the profile information. Yeah. All right, so I guess I'll probably stop here and not talk about the galaxy stuff. I had some interesting comments about like interesting aspects regarding the recent James Webb observations of very early galaxies. But let me stop here, and then if there are questions, I can talk about this more. So yeah, so just to summarize, these very heavy particles, they get produced during inflation, and then there are interesting signatures. And if you do very simple searches, they can already get to like order 10 of, they can already look for order 10 of these spots on the sky. But of course, the important things here are to do an actual search with the data, take into account these point sources, and also follow up with similar studies in the context of galaxies. So yeah, with that, let me conclude, and thanks a lot for your attention.
Say that these particles have to be strongly coupled.
Because of order 1 Gs or larger.
G6.
Yeah, so good. So again, this is something that is dependent on this particular search. So this, of course, like this, yeah, this is pretty big. This is not still, I'd say, not as big as 4 pi if you want. It's not like the Utrecht bound or something like that. But we wanted to have a case study where the position space search can do better than the power spectrum search. So that's why like the G of 6 serves as a good example. But we did have other examples where like G of even order 2 would work. And in the follow-up study that we focused on, we had the same concerns. We basically did not use these values of G. So if you use a neural net based search, then you can even go to like G of order 1, like 1 point something, and that's also fine. Yeah, but you just need powerful detection techniques in that case. Yeah.
Sorry, just one question. What's the multiple of CMB beyond, like, what's the maximum multiple of CMB beyond which you're not allowed to have galaxy formation? You said the 100-ish multiple is the easier term, right?
Yeah, good. So
And so you have overdensity present there, and then
right.
later will get into horizon, and then this will have more delta than the other places, meaning you have more higher chance of having galaxy formation there. Then I'm wondering, like L100 is that allowed to have the galaxy?
No, it's
No,
it's
but then what's
good. So I should not say it is not allowed to have the galaxy. I mean, you can have that. But the point is, if you wanted to probe a cosmological mode with like L of 100 or a certain eta star, then CMB is just a more powerful probe because we have measured it so well. So equivalently large. I mean, 100 megaparsec, it's kind of on the borderline because it's right at the BAO scale, right? So you still have useful information from the matter power spectrum, for example. But if you go to even smaller values of L, then those start, yeah, then CMB is just more precise and more powerful. But equivalent, like if you were to go to even larger L, that's where the matter power spectrum starts becoming more useful. So yeah, so there is some degree of complementarity that is there. For example, like the thing that we are, well, I guess I do have some plots over here for the galaxy study. So here we are talking about much smaller values of eta star compared